Okay, so we are looking at this dual spool turbojet engine, and we have looked at with afterburner calculations, and now look at the performance parameter. So this is where we have just stopped. We just checked both the different scenario with or without afterburner, and we have stopped here. So now we will look at some of the performance parameter like for the dual spool engine. Like one of the important parameter is the specific thrust, which would be again 1 plus F plus FAB into V9 minus V plus A9 by M dot A P9 minus PA. Now once we get that, we can also find out the TSFC, like TSFC would be M dot F plus M dot FAB by T. So this can be written at F plus FAB 1 plus F plus FAB into V9 minus V plus A9 by M dot A P9 by PA. So obviously when the afterburner is not on, then this term means FA. So without AB, FAB would be 0. Now also it resembles now the propulsive efficiency eta P, which will be TV by TV plus half M dot E V minus V square. So where the M dot E is the exit velocity, exit mass flow rate, exit velocity, and similarly we can write thermal efficiency, which is TV plus half M dot E VE minus V square by M dot FQR. Okay. So now the overall efficiency would be eta P into eta thermal efficiency. So that's how you can find out. So finally when you get this thermodynamical analysis, final aim is to find out the like getting this performance parameter like specific thrust, TSFC and all this. Now moving ahead, there would be another thing which I would like to discuss about of the something like micro turbojet. So these are basically small turbojet engine. There is a cross section of this picture which is a engine of SR30. This is SR30, this is a cross section of micro turbojet, and you can see the different components of that engine. So these are the small turbojet engines which are developed for use in cruise missile, target drones and other small unmanned air vehicles. Like there are multiple examples of this. This is one of the micro turbojet which the first commercial micro turbine were made available by JPX in the early 1990s. And right after that, shortly after that, Germany and Netherlands sought out to develop powerful lightweight fuel micro turbine. Now also these are the some micro turbine engines which you can see which are there, and this is one of the example of that micro turbine. Rather, let us say this is the Harpoon missile which is in air to surface or submarine launch anti-surface or anti-ship missile. It is powered by a small CAE J402 small turbojet engine which has a solid propellant booster. So which is now you can see this, there are also range of micro turbine which are available in the market, and they are sort of used to for this kind of applications. Now, with that we will move to turbofan. So, this is now the engine which will have, we have seen already multiple example of this kind of engines where there would be a fan associated with. So, with the turbojet we have added fan, and this fan is going to have some bypass, and then like one can divide the turbofan engine is different ways. One can have like it's divided into two ways, like whether forward fan or aft fan, that is one. Then forward fan can be taken again into different ways, like mixed fan and core flow, mixed fan core flow, mixed fan plus core flow, or it could be unmixed, right, and unmixed flow. And then if it is unmixed, again it could have short duct, or it could be having a long duct. Okay. Then again forward fan, it could have some another branching, could be single spool. Then if we have two spool, then we could have three spool also. Okay. And then all these things can be clubbed to have two more segment. One could be geared fan or ungeared fan. Okay. Then the aft fan can no, then again this is another way one can classify high bypass ratio engine, or this could have low bypass ratio. Now, low bypass ratio, it could be with AB or it could be without AB, that means with and without afterburning. So, there are different category of engines which are available, and bypass ratio, when you talk about this bypass ratio, that means we talk about this factor. So, the bypass ratio beta we called is the bypass BPR, bypass ratio, which is m dot cold by m dot hot. So, that means the hot, so this could be m dot fan by m dot core. So, how much pass through the engine and how much being there. So, that is what it is there. So, now in the turbojet, so let us have a layout of a engine. Let us say start with this, it goes like this, then I will have this, it comes so this goes up and this, then I can have another one here which is connected like this, in between I have this. So, this one is connected and this is the nozzle, this is the nozzle. Okay. So, there are different stations. Now, let us say this is A, this is 2, then this is 3, this is 4, this is 5, this is 6, this is 7, 8, this is 9, this could be 10, this could be 11. So, this is a double spool layout, double spool where fan, double spool system where the fan plus LPT, LPC are driven by the LPT and HPC is driven by HPT. Here is the fan, then after that some portion of the air goes to the core, some goes here, this is bypass, then it is high pressure, low pressure compressor, high pressure compressor, then low pressure, high pressure turbine, low pressure turbine, then if AB is there it would be sitting there. Now, so already now we can look at the TS diagram. So, here let us say start with A. So, this is A, we go to 2, then we go to somewhere 3, then 3 to 4, then we go to 5, 5 to 6 to 7, if there is no after burning it is 8, 8 to 9, and this is 10, where 10 to this is 11. So, this is how it looks like. Now, we can do the analysis intake. So, we are not going to repeat the same exercise here, because the intake would be exactly the similar like what we have done in the turbojet. Then we have fan. Now, a similar analysis to the compressor it can be done. So, you can see the fan pressure P10 would be P02 into pi F, which is the fan pressure ratio. Then we can find the T010 is T02 1 plus pi F gamma minus 1 by gamma divided by eta F. So, that is the fan efficiency, that is pi F is the pressure ratio. Then we have low pressure compressor. So, this is P03, which would be P010 into pi LPC. So, and similarly T03 would be T010 1 plus pi LPC to the power gamma minus 1 gamma by 1 eta LPC. Then we have HPC, which we could find out the HPC, and then HPC would be similar like P04 would be P03 into pi HPC. So, T04 would be T03 1 plus pi HPC to the power gamma minus 1 by gamma minus 1 by eta HPC. So, that is what we can do, and Then 5 we go to combustion chamber, where again similarly we find out P naught 5 would be P naught 4 minus delta P combustion chamber. That means P naught 5 is P naught 4 1 minus delta P Cc. Now, the temperature of the outlet of the combustion chamber is also to the inlet to the turbine, and that will dictate the other constraint Cph by Cpc T naught 5 by T naught 4 minus 1 eta b Qr by Cpc T naught 4 minus Cph by Cpc T naught 5 by T naught 4. So, this again from the energy balance we get it. Then we go to HPT. So, HPT is going to run the HPC. So, similarly we dot m dot a. So, we again assume WHPC would be lambda 1 eta m1 WHPT. So, which allows us to write m dot Cpc T naught 4 minus T naught 3 eta m1 lambda 1 m dot a 1 plus f Cph T naught 5 minus T naught 6. So, the T naught 6 by T naught 5, this is 1 minus Cpc by Cph into T naught 3 lambda 1 eta m1 1 plus f T naught 4 by T naught 3 minus 1. So, here also eta m1 is the mechanical efficiency, HPC spool mechanical efficiency, and the percentage of the HPT which developed, the lambda 1 would go there to run the. So, what we will get? So, we will get the P naught 6 is P naught 5 1 minus T naught 5 by T naught 6 eta HPT into T naught 5, which is gamma h by gamma h minus 1. Now, we will go LPT. So, again here the low pressure compressor, this is the both fan and the low pressure compressor would be driven by that. So, we can write W fan plus W LPC is lambda 2 eta m2 W LPT, which allow us to write the beta m dot a Cpc T naught 10 minus T naught 2 plus m dot a Cpc T naught 3 minus T naught 2 eta m2 m dot a 1 plus f T naught 6 minus T naught 7. So, we can do bit of algebra here, like we can write 1 plus beta m dot a Cpc T naught 10 minus T naught 2 plus m dot a Cpc T naught 3 minus T naught 10 equals to lambda 2 eta m2 m dot a 1 plus f Cph T naught 6 minus T naught 7. So, what we will get? T naught 7 equals to T naught 6 minus Cpc lambda m2 eta m2 lambda 2 eta m2 1 plus F Cph into 1 plus beta T naught 10 minus T naught 2 plus T naught 3 minus T naught 10, and the pressure at the outlet will get P naught 6 1 minus T naught 6 minus T naught 7 by eta LPT into T naught 6 gamma H by gamma H minus 1. Now, if there is a bleed from the high pressure compressor, if there is an air bleed from the HPC at station where the pressure is P naught 3B, then the energy balance with high pressure turbine would give the so what we can have that if there is a bleed, then let us say at station where the pressure is P naught 3B, then the energy balance would be m dot C Cpc T naught 3B minus T naught 3 plus m dot A into 1 by B 1 minus B Cpc T naught 4 minus T naught 3B equals to lambda m1 lambda 1 eta m1 m dot A 1 plus F minus B Cph T naught 5 minus T naught 6, where B is the bleed ratio, which is m dot B by m dot A, defining the bleed air from the HPC to the core air flow. Moreover, such a bleed has its impact on the energy balance of the low pressure spool and air passing through the low pressure turbine, which is also now reduced. That means what we can do also in the low pressure turbine LPT, in the LPT section 1 plus beta m dot A Cpc T naught 10 minus T naught 2 plus m dot A Cpc T naught 3 minus T naught 10 equals to lambda 2 eta m2 m dot A 1 plus F minus B Cph T naught 6 minus T naught 7. So, if there is a bleed, then the whole analysis between that station has to be changed. Now, the flow in the jet pipe is frequently associated with the pressure drop, mainly due to the skin friction. So, the pressure upstream of the turbine nozzle is slightly less. So, what we can get P naught 8 would be P naught 7 1 minus delta P jet pipe, and T naught 8 would be T naught 7. Now, finally, we come to the nozzle. This is hot nozzle, let us say. So, here the exhaust velocities in both the hot gases from the turbine nozzles are obtained. After again we have to check whether it is choke or not. So, typically we will see Pc 1 by 1 minus 1 by eta nozzle 1 gamma H minus 1 gamma H plus 1 gamma H by gamma H minus 1. So, for an ideal case eta n was 1. So, this would be reducing to gamma H plus 1 by 2 gamma H by gamma H minus 1. Now, if Pc is greater than Pa, then the nozzle is choked and the temperature pressure of the gases leaving the nozzle are critical values. So, T9 would be Tc, P9 would be Pc, which is obtained like T naught 8 by T9 is gamma H plus 1 by 2, and V9 would be root over gamma H or T9. Or if it is unchoked, then P9 equals to Pa, then V9 is 2 Cph T naught H eta Nt 1 minus Pa by P naught gamma H minus gamma H. So, the pressure ratio in the nozzle which could be obtained P naught 8 by Pa, it is like P naught 8 by P naught 7, P naught 7 by P naught 6, P naught 6 by P naught 5, P naught 5 by P naught 4, P naught 4 by and so on, P naught 3 by P naught 2, sorry P naught 10, 3, then P naught 10 by P naught 2, P naught 2 by P naught A, P naught A by Pa. So, this is how we get, and then there is fan nozzle, or one can say the cold nozzle which is there, and there also critical pressure has to be checked, where P naught 10 by Pc 1 by 1 minus eta fan nozzle, gamma c 1 gamma c plus 1 gamma c by gamma c minus 1. So, again for an ideal nozzle, for an ideal nozzle, gamma Fn eta Fn would be 1. So, this guy Pc becomes gamma c plus 1 by 2 gamma c by gamma c minus 1. If Pc greater than Pa, it is choked nozzle. So, T11 would be Tc, P11 would be Pc. So, T naught 10 by T11 would be gamma c plus 1 by 2, and exit velocity would be gamma c r T11. If unchoked, then P11 would be Pa, then the exit velocity would be calculated at 2 Cpc T naught 10 eta fan nozzle 1 by Pa by P naught 10 gamma c minus 1 by gamma c, and P naught 10 by Pa is P naught 10 by P naught 2, P naught 2 by Pa. So, the net thrust force which is can be now calculated, there would be two component of that. So, the specific thrust will have 1 plus F V9 plus beta V11 minus U 1 plus beta by 1 by m dot A11 P11 minus Pa plus A9 P9 minus Pa, which one can write 1 plus F V9 plus beta V11 minus U 1 by m dot A11 P11 minus Pa A9 P9 minus Pa. So, that is out, and specific thrust can be calculated. So, one can do that, which is T by let us say the total mass flow rate, which is m dot At, and which is nothing but T by m dot H plus m dot C, which is T by m dot A1 plus beta. So, which one can write 1 plus F by 1 plus beta V9 plus beta by 1 plus beta V11 minus U plus 1 by m dot 1 plus beta A11 P11 minus Pa A9 P9 minus Pa, and TSFC, which would be m dot F by T, which is m dot F. So, which one can write F by T m dot A. So, this is how all the performance parameter for this double spool engine one can calculate along with all this information. So, what we have looked at both for the turbojet and turbofan, What is important is that the station wise calculation, you have to pressure, temperature, you have to find out, and in the actual cycle there would be losses. So, you need to consider their efficiencies, and by considering their efficiencies, once you calculate this pressure, temperature, finally you come down to the nozzle, and then you first thing you check whether the nozzle is choked or unchoked. Accordingly, you get the exit velocity and then put it back in the thrust and get all the thermal efficiency, specific thrust, TSFC and all this. So, we will stop here and continue the discussion in the next lecture.